What if I told you that for every atom in your body, there exists a perfect mirror image somewhere in the universe, an identical twin made of the same stuff, but with one crucial difference that makes it the most dangerous substance known to science? This isn't science fiction. This is antimatter, and it's been hiding in plain sight since the very beginning of time. Now, before we dive into this rabbit hole together, I need to ask you something. Have you ever wondered why you exist at all? I mean, really thought about it? Because according to the laws of physics, you shouldn't be here. None of us should. The universe should be empty, cold, and completely lifeless. The fact that you're watching this right now is actually one of the greatest mysteries in all of science. My name is Alex, and I've spent the last 3 years diving deep into the most mind-bending concepts in physics. And antimatter might just be the strangest one yet. In this video, I'm going to reveal why antimatter is called the mirror of reality, why a single gram of it could power your house for decades, and most importantly, why the existence of antimatter threatens everything we think we know about the universe itself. But here's where it gets really wild. I've discovered something that most people don't realize about antimatter. It's not just some exotic substance locked away in particle accelerators. It's being created right now above your head in the atmosphere. It's being produced inside your own body at this very moment. And somewhere out there in the cosmos, there might be entire galaxies made of the stuff, invisible to our telescopes but very, very real. What I'm about to show you will completely change how you see reality, because antimatter isn't just the opposite of matter, it's the key to understanding why anything exists at all. And by the end of this journey, you'll understand why some scientists believe that antimatter might be the most important discovery in human history. So let's start with something that sounds simple, but will blow your mind once you really think about it. Imagine you're looking in a mirror. You see yourself, but everything is reversed. Your right hand appears to be your left hand. Any writing on your shirt is backwards. It's still you, but it's you flipped in a very specific way. Now, what if I told you that every single particle in the universe has a mirror image just like this? Not just similar, but absolutely identical in every way except for one fundamental property. This is the basic idea behind antimatter. For every electron, there's an anti-electron called a positron. For every proton, there's an anti-roton. For every neutron, an anti-neutron. These antiparticles have exactly the same mass as their normal matter counterparts, exactly the same size, exactly the same behavior, but their electric charge is flipped. Where an electron has a negative charge, a positron has a positive charge. Where a proton is positive, an anti-roton is negative. It sounds almost trivial, doesn't it? Just flip a sign here and there and you've got antimatter. But this tiny difference creates the most explosive reaction possible in our universe. When matter and antimatter meet, they don't just react like hydrogen and oxygen making water. They don't combine like sodium and chlorine making salt. They completely annihilate each other, converting their entire mass directly into pure energy. According to Einstein's famous equation E=mc², let me put this in perspective for you. When you burn gasoline in your car, you're converting about 1/billionth of its mass into energy. Nuclear fusion, the process that powers the sun, converts about 0.7% of mass into energy. But when matter and antimatter annihilate, 100% of their mass becomes energy, 100%. It's the most efficient reaction possible in the universe. A single gram of antimatter annihilating with a gram of matter would release as much energy as the bomb dropped on Hiroshima. Just 2 g of material, and you've got the power of a nuclear weapon. Scale that up to a kilog and you're talking about energy equivalent to 43 megatons of TNT. That's more than the largest nuclear bomb ever detonated. But here's what really gets me. This isn't just some theoretical calculation. This actually happens right now in particle accelerators around the world. Scientists are creating tiny amounts of antimatter and watching it annihilate with regular matter. We've seen this reaction, we've measured it, we've harnessed it, and it works exactly as the equations predict. Now you might be thinking, okay, that's cool, but where does antimatter come from? But how do we make it? And that's where the story gets really interesting, because antimatter isn't just something we create in labs, it's everywhere. Every second, cosmic rays from deep space are slamming into our atmosphere at nearly the speed of light. These high-energy particles collide with atoms in the air, and in those violent collisions, pairs of particles are born. Matter and antimatter created together in equal amounts. Right now above your head, positrons are being created and immediately annihilating with electrons in the atmosphere. It's happening constantly. An invisible fireworks show powered by the universe itself, but it gets even stranger. Your own body is creating antimatter. Certain radioactive elements naturally decay by emitting positrons. Potassium-40, which exists in every banana you've ever eaten, occasionally spits out a positron. Carbon-11, which is used in medical imaging, is a positron emitter. There are people walking around with radioactive traces in their bodies right now, glowing with antimatter reactions. And then there are the truly mind-blowing sources. Lightning creates antimatter. When those massive electrical discharges tear through the atmosphere, they create conditions so extreme that matter and antimatter pairs pop into existence. Some scientists think that every lightning bolt on Earth is accompanied by a brief flash of antimatter annihilation. But perhaps the most incredible source of all is black holes. Stephen Hawking predicted that black holes should emit radiation as they evaporate, and part of that radiation should be antimatter. We're talking about objects so massive that they bend space-time itself, and they're spewing out the mirror image of reality. Now here's where we run into the biggest mystery in all of physics. If matter and antimatter are created together in equal amounts, if the universe started with a perfect balance of both, then where did all the antimatter go? This is called the matter-antimatter asymmetry problem, and it's one of the deepest puzzles in science. In the early universe, just after the Big Bang, matter and antimatter should have been created in exactly equal quantities. They should have immediately annihilated each other, leaving behind nothing but pure energy. The universe should be empty. No stars, no planets, no galaxies, no you. But obviously that's not what happened. Somehow, somewhere in those first few moments after the Big Bang, the universe cheated. For every billion pairs of matter and antimatter particles that annihilated each other, there was one extra matter particle left behind, just one in a billion. That tiny imbalance, that minuscule asymmetry is the reason everything exists. Think about that for a moment. You, me, every star in the sky, every planet we've ever discovered, every atom in every living thing. We're all made from the leftover scraps of a cosmic annihilation event. We exist because the universe somehow managed to save a fraction of a percent of matter from total destruction. But what caused this imbalance? Why did matter win out over antimatter? This is where things get really speculative, really exciting, and really weird. Some physicists think the answer lies in something called CP violation. That's a fancy way of saying that the laws of physics might not be perfectly symmetric. Maybe under certain extreme conditions, matter and antimatter don't behave exactly the same way. Maybe there's a subtle preference built into the fabric of reality itself. Others think the answer might involve extra dimensions. What if our three-dimensional universe is just a slice of a much larger, higher-dimensional space? What if antimatter doesn't disappear, but instead gets banished to a parallel reality that we can't see or touch? And then there are the really wild ideas. What if time itself played a role? What if the universe went through a period where time flowed differently, where cause and effect worked in reverse, where the normal rules of physics were suspended long enough for matter to gain the upper hand? But here's what really keeps me up at night thinking about this. What if the antimatter didn't disappear? What if it's still out there? Imagine for a moment that somewhere in the vast cosmos there are entire galaxies made of antimatter, stars burning anti-fuel, planets orbiting anti-stars, maybe even life forms made entirely of antiparticles. From a distance, these antimatter galaxies would look identical to normal matter galaxies. Light is its own antiparticle. So photons from an antimatter star would be indistinguishable from photons from a regular star. The only way we'd know is if matter from our galaxy somehow encountered antimatter from one of these hypothetical antilaxies. And when that happened, the result would be the most spectacular explosion in the history of the universe. We're talking about gamma rays so intense they could sterilize entire solar systems. Energy releases that would make supernovas look like birthday candles. Some astronomers are actually looking for evidence of this. They're scanning the sky for the telltale signature of matter-antimatter annihilation on a cosmic scale. So far, they haven't found anything definitive. But the search continues because if antimatter galaxies do exist, they would revolutionize our understanding of the universe. Now you might be wondering, if antimatter is so dangerous, so explosive, how do scientists work with it? How do you store something that annihilates the moment it touches any normal matter? The answer is both elegant and incredibly complex. You use magnetic fields. Since antimatter particles are electrically charged, they can be trapped and held in place by carefully designed magnetic bottles. Imagine invisible magnetic walls that keep the antimatter suspended in a perfect vacuum, never touching the sides of its container. The largest antimatter trap in the world can hold about 10 million antirotons. That sounds like a lot until you realize that 10 million antirotons have a mass of about 16 F2. A fem is 1/4 of a gram. To put that in perspective, the period at the end of this sentence contains about 50 billion times more matter than the world's largest antimatter trap. Creating antimatter is also incredibly expensive and inefficient. It costs about $25 billion to make a single gram of positrons. That makes antimatter the most expensive substance on Earth by a factor of about 1 trillion. Even gold at current prices would cost less than 1/1000th of 1 cent per gram compared to antimatter. And the energy efficiency is terrible. For every unit of energy you put into creating antimatter, you get back maybe 1/100000th of that energy when it annihilates. It's like paying $1 million for a battery that stores $1 worth of electricity. But despite these limitations, scientists continue to study antimatter because it might hold the key to understanding the deepest mysteries of existence. Why do we have something instead of nothing? What happened in those first moments after the Big Bang? Are there hidden symmetries in nature that we haven't discovered yet? Some researchers are even exploring practical applications. Could we use antimatter as fuel for spacecraft? A few grams of antimatter could theoretically propel a spaceship to nearby stars in just a few decades. Could we use it for medical treatments? Antimatter particles can be precisely targeted to destroy cancer cells without damaging healthy tissue. But all of these applications are still decades or centuries away. For now, antimatter remains one of the most mysterious and fascinating subjects in all of science. And this brings us to something that absolutely blew my mind when I first learned about it. Remember how I said antimatter is like looking in a mirror? Well, it turns out that analogy goes way deeper than just flipped electric charges. The relationship between matter and antimatter reveals something profound about the very structure of reality itself. See, in physics we have this concept called symmetry. And symmetry isn't just about things looking pretty or balanced, it's about the fundamental laws that govern how the universe works. When physicists talk about symmetry, they're talking about operations you can perform on a system that leave it unchanged. Rotate a perfect sphere, and it looks exactly the same. Reflect a snowflake and you get an identical pattern. But here's where antimatter gets really weird. It's connected to 3 different types of symmetry that when combined, seem to be perfectly preserved in nature. These are called C, P, and T symmetries. C stands for charge conjugation, which is basically swapping particles for antiparticles. P stands for par, which is like looking in a mirror, flipping left and right. And T stands for time reversal, running the clock backwards. Now individually, these symmetries can be broken. Nature does seem to have a slight preference for left over right in certain situations. Some particles decay in ways that violate par. And we already talked about how charge symmetry is broken since we have more matter than antimatter. But here's the incredible part. When you combine all 3 operations together, CPT symmetry appears to be perfectly preserved always. What this means is that if you take any physical process, swap all the particles for antiparticles, flip it in a mirror, and run it backwards in time, you get a process that's just as valid as the original. It's like the universe has this deeper level of symmetry that remains unbroken no matter what we throw at it. But think about what this implies. If CPT symmetry is truly fundamental, then somewhere in the mathematical structure of reality, matter and antimatter are just different perspectives on the same underlying truth. They're not separate things. They're different faces of a single deeper reality that we can only see pieces of at a time. This gets even stranger when you consider what happens at the quantum level. In quantum field theory, which is our best description of how particles behave, every particle is really just an excitation in an underlying field that fills all of space. The electron field, the proton field, the photon field, these fields are like invisible oceans, and particles are like waves on the surface. But here's the kicker. Antimatter particles aren't separate excitations in separate fields. They're the same fields just vibrating in the opposite direction. It's like the difference between a wave moving left and a wave moving right on the same string. Same string, same physics, just pointing different ways. And this leads to one of the most mind-bending ideas in all of physics. What if antiparticles aren't really separate entities at all? What if they're just regular particles moving backwards through time? I know that sounds insane, but hear me out. This idea was proposed by physicist John Wheeler and his student Richard Feynman back in the 1942. They suggested that a positron, an anti-electron, is actually just an electron that's moving backwards through time. When you see matter and antimatter annihilate, you're not seeing 2 particles destroy each other, you're seeing one particle change direction in time. Picture this. An electron is moving forward through time, minding its own business. Then something happens, some interaction that causes it to reverse direction and start moving backwards through time. To us, watching from our forward-moving perspective, this backwards-moving electron looks like a positron. It has the opposite charge because we're seeing everything in reverse. Now, I'm not saying this is definitely how antimatter works. There are problems with this interpretation, and most physicists today think of antiparticles as genuinely separate entities. But the fact that this idea even makes mathematical sense tells you something profound about the nature of time and reality. And speaking of time, here's something that'll really mess with your head. In our everyday experience, time has a direction. We remember the past, we don't remember the future, eggs break, they don't unbreak, hot coffee cools down, it doesn't spontaneously heat up. But at the fundamental level, at the level of individual particles, time doesn't seem to have a preferred direction at all. If you filmed an electron bouncing around in empty space and played the video backwards, you couldn't tell the difference. The laws of physics work exactly the same way, forwards and backwards. It's only when you get to large collections of particles, when statistical effects start to dominate, that time develops an arrow. This is deeply connected to the antimatter mystery. If the fundamental laws of physics are perfectly time-symmetric, then the Big Bang should have created equal amounts of matter and antimatter. The fact that it didn't means that something broke time symmetry in those first moments after the universe began, something that we still don't understand. But here's where things get really speculative, really exciting. What if the solution to the antimatter puzzle isn't that antimatter disappeared? What if it's that antimatter is still here, but we're looking for it in the wrong place? Some theories suggest that our universe might be just one of many. Not just other galaxies or other regions of space, but entirely separate universes with their own laws of physics, their own space and time. In some of these theories called multiverse theories, our universe and a mirror antimatter universe could have been created together at the Big Bang like cosmic twins. In this anti-matter universe, everything would be made of antiparticles, anti-atoms forming anti-molecules, forming anti-planets orbiting anti-stars. And if there were life in such a universe, it would be anti-life made of antiparticles, but following the same chemical and biological processes we see in our own universe. From their perspective, we would be the anti-matter universe. They would think of themselves as being made of normal matter, and they would wonder where all their antimatter went. It's a perfect symmetry, a cosmic mirror that solves the asymmetry problem by simply putting the missing antimatter somewhere we can't see it. Now, I want to be clear, this is highly speculative. We have no direct evidence for antimatter universes or multiverses of any kind, but the math works out and it's a beautiful solution to one of physics's biggest puzzles. And there's another possibility that's even stranger. What if antimatter isn't missing at all? What if it's hiding in plain sight and we just don't know how to see it? This idea comes from some cutting-edge theories about the nature of gravity in spacetime. We know that antimatter has positive mass, just like regular matter. But what we don't know for certain is exactly how antimatter behaves in a gravitational field. Now, almost everyone expects that antimatter should fall down just like regular matter, drop an anti-apple and it should fall away from it. But here's the thing. We've never actually tested this. We've never dropped antimatter in Earth's gravity to see what happens. The reason is simple. We can barely make any antimatter at all. And what little we can make is stored in magnetic traps in perfect vacuums. You can't exactly take it outside and drop it, but several experiments are being planned to test this, and the results could be revolutionary. What if antimatter falls up instead of down? What if it has some kind of repulsive gravitational effect? This would explain why we don't see antimatter in the universe. It's not that it was destroyed or banished to another dimension, it's that it was gravitationally expelled from matter regions like galaxies and solar systems. In this scenario, there could be vast clouds of antimatter floating in the empty spaces between galaxies, invisible to our telescopes because there's no regular matter nearby for it to annihilate with. It would be dark matter, but not the kind of dark matter we usually talk about. It would be dark because it doesn't interact with light in ways we can detect, but it would still be made of familiar particles, just antiparticles. This is still extremely speculative, and most physicists expect that antimatter will behave just like regular matter in a gravitational field, but until we test it, we won't know for sure. And that's what I love about science. There are still fundamental questions about reality that we haven't answered yet. But let's get back to something we can test, something we can measure, the practical applications of antimatter. Because despite all the theoretical mysteries and speculative ideas, antimatter is real. We can make it, we can store it, and we can use it. The most immediate application is in medicine. Right now, doctors use a technique called positron emission tomography or PET scans to look inside your body. They inject you with a radioactive tracer that emits positrons. When those positrons encounter electrons in your body, they annihilate and produce gamma rays. By detecting those gamma rays, doctors can create detailed images of your organs and tissues. This isn't science fiction. This is happening in hospitals around the world every day. Antimatter is being used to diagnose cancer, heart disease, and neurological disorders. It's saving lives right now, but the potential goes far beyond medical imaging. Researchers are exploring whether beams of anti-roton could be used to treat cancer more precisely than current radiation therapy. The idea is that anti-roton could be targeted directly at tumor cells where they would annihilate and release their energy exactly where it's needed without damaging healthy tissue. And then there's space travel. This is where antimatter gets really exciting from a practical standpoint. Chemical rockets, the kind we use to get to the moon and Mars, are incredibly inefficient. They can only achieve a small fraction of the speed of light, which means that trips to even the nearest stars would take thousands of years. Nuclear rockets are better, but they're still limited by the amount of energy you can extract from nuclear reactions, but antimatter rockets could in principle achieve significant fractions of the speed of light. We're talking about trips to nearby stars in decades instead of millennia. The numbers are staggering. A spacecraft powered by matter-antimatter annihilation could theoretically reach about 10% of the speed of light. At that speed, you could reach Proxima Centauri, the nearest star. In about 40 years, Alpha Centauri would be a 43-year journey. Suddenly, interstellar travel goes from impossible to merely extremely challenging. But here's the catch. Remember those cost figures I mentioned earlier? $25 billion per gram of antimatter to fuel a spacecraft to the nearest star. You'd need maybe 100 G of antimatter. That's $2.5 trillion just for the fuel. And that's assuming we could make antimatter 1,000,000 times more efficiently than we can today. So, we're not booking tickets to Alpha Centauri anytime soon, but the potential is there. And as our technology improves, as we learn more about antimatter production and storage, these dreams might become reality. There's also the possibility of using antimatter for power generation here on Earth. A few grams of antimatter could power a city for years. No carbon emissions, no nuclear waste, just pure energy from the most efficient reaction in the universe. But again, the practical challenges are enormous. Not just the cost and difficulty of production, but the safety issues. How do you safely transport and store a substance that could level a city block if containment fails? How do you prevent it from being weaponized? These are problems that don't have easy solutions. Yet despite all these challenges, research continues. Because antimatter represents something more than just another energy source or propulsion system. It represents our quest to understand the deepest mysteries of existence. Why is there something rather than nothing? What happened in those first moments after the Big Bang? Are there hidden symmetries and structures in reality that we haven't discovered yet? Every time we create an anti-roton in a particle accelerator, every time we trap a positron in a magnetic field, we're probing these fundamental questions. We're looking into the mirror of reality and asking what it can teach us about ourselves and our universe. And there's something deeply moving about that. Here we are, collections of atoms that somehow became conscious, using our intelligence to create and study the mirror image of our own substance. We're matter studying antimatter. We're the universe investigating its own reflection. In the next part of our journey, we're going to dive even deeper into these mysteries. We're going to explore what happens when you try to make antimatter atoms, not just individual antiparticles. We're going to look at the most ambitious experiments ever conceived. Projects that are trying to answer whether antimatter falls up or down, whether anti-ATOS can form antimacules, and whether there might be entire antimatter solar systems hiding in the dark spaces between stars. Because the story of antimatter isn't just about physics, it's about the nature of existence itself, and we're just getting started. But before we dive into those incredible experiments, I need to tell you about something that happened in 1995 that changed everything. For the first time in human history, scientists at CERN didn't just create individual antiparticles. They created actual anti-atomy of anti-matter. Think about what this means for a second. An atom is a complex system. You've got a nucleus made of protons and neutrons surrounded by electrons in specific energy levels. The whole thing is held together by electromagnetic forces following the rules of quantum mechanics. It's like a tiny solar system, except instead of gravity, it's electric charges keeping everything in orbit. Now imagine building that same structure but with antiparticles, antirotons, and antineutrons forming an antinucleus, with positrons orbiting around it. Every charge is flipped, but the structure remains identical. It's like constructing a perfect architectural replica of a building, but using materials that would explode if they ever touched the original. The team at CERN managed to create 9 anti-hydrogen atoms, just 9. They existed for about 40 billionth of a second before annihilating with regular matter. But in those brief moments we had actual antimatter atoms floating in our universe. And here's what absolutely blows my mind about this achievement. Those anti-hydrogen atoms behaved exactly like regular hydrogen atoms. Same energy levels, same spectral lines, same quantum mechanical properties. It was like looking at a perfect twin, identical in every way except for the fundamental charge of its components. But creating anti-ATOS opened up possibilities that individual antiparticles never could, because now we could start asking questions that get to the heart of reality itself. Do anti-ATOS emit light the same way regular atoms do? Do they respond to magnetic fields identically? And most importantly, how do they behave in Earth's gravitational field? That last question is the big one, because if antimatter falls upward instead of downward, it would revolutionize our understanding of gravity, space-time, and the structure of the universe. It would suggest that there's something fundamentally different about antimatter that we've never suspected. Now most physicists expect antimatter to fall down just like regular matter. Einstein's theory of relativity predicts that antimatter should have positive mass and should be attracted to gravitational fields just like anything else. But here's the thing about science: it doesn't matter what we expect. It doesn't matter what our theories predict. What matters is what actually happens when we test it. And that's exactly what researchers at CERN are trying to do right now with an experiment called ALPHA. They're creating anti-hydrogen atoms, trapping them in magnetic fields, and then very carefully releasing them to see which way they fall. It sounds simple, but it's one of the most technically challenging experiments ever attempted. The problem is that antimatter is incredibly difficult to work with. Remember, these anti-atoms can't touch anything of regular matter, or they'll annihilate instantly. So you have to create them in a perfect vacuum, trap them with magnetic fields, and then measure their motion with incredible precision. And the effects you're looking for are tiny. Earth's gravity is the weakest of all the fundamental forces. The gravitational pull on a single anti-hydrogen atom is so small that it's easily overwhelmed by any stray magnetic fields, air currents, or vibrations in the equipment. It's like trying to measure the weight of a feather in the middle of a hurricane. But if they succeed, if they can definitively show that antimatter falls in Earth's gravitational field, it will be one of the most important experimental confirmations in the history of physics. And if they discover that antimatter falls upward, well, that would change everything. Because think about what that would mean. If antimatter has anti-gravity properties, then the missing antimatter from the Big Bang might not be missing at all. It might have been gravitationally separated from regular matter in the early universe. While matter clumped together to form galaxies and stars, antimatter might have been pushed outward into the vast empty spaces between galactic clusters. This could solve the antimatter asymmetry problem in a completely unexpected way. Instead of antimatter being destroyed or banished to another dimension, it could be hiding in the cosmic voids, forming its own structures that we can't see because there's no regular matter nearby for them to annihilate with. Imagine vast anti-matter galaxies floating in the darkness between our own galaxy clusters. Anti-stars burning anti-fuel anti-planets orbiting in anti-solar systems. From a distance, they would be completely invisible to us because light itself doesn't distinguish between matter and antimatter. The only way we'd know they were there is if some regular matter somehow drifted into one of these antimatter regions and created a massive annihilation event. And here's something that gives me chills when I think about it. If antimatter galaxies do exist, and if they contain anti-life, then right now somewhere in the universe there might be anti-beings made of anti-particles living on anti-worlds wondering where all their matter went. They would think of themselves as being made of normal matter. To them, we would be the anti-matter beings. They might be conducting their own experiments trying to understand why their universe seems to be dominated by what they call matter, wondering what happened to all the antimatter they expected to find. It's a perfect symmetry that solves the cosmic puzzle by simply putting each type of matter where the other can't see it. And the beautiful thing is both sides would be equally puzzled by the same mystery. But let's get back to what we can actually test.